Hello everybody, welcome to another IZ80DWF arcade repair video. This is the second one in the Atari Pole Position Repair-a-thon series. If you haven't seen the first repair of the series, I suggest you to watch it before this one, since most prerequisite information will be given for granted. A link to it is down in the description. This video will show the repair process of a Pole Position Revision E boardset. As we have seen on the first video of the series, this is one of the boards that in place of the 16-bit CPU's Z8002, it has instead a couple of Z80 processors. Of course, I've substituted them with the correct ones. These are the East Germany clones of the Z8002 that I've just received. This CPU board also has an empty socket in position 7C and a missing Q2 transistor nearby that appears to have been just cut off. This may have been done during a previous repair attempt. However, Q2, according to the schematic, is a very common 2N3904, so I'm going to replace it with a spare one. The 7C missing IC is the main address decoder PLD for the Z80 CPU, which is the third processor on a pole position board. This very same address decoder replacement was also shown in the first video, so I've just programmed another 16V8 chip and installed it in the socket. Another very important step that often shows hidden problems is to check all socketed ICs, in other words, all ROMs, some static RAMs, and the NAMCO custom ICs, like the one in this picture. Notice that pin number 1 of this IC was not correctly inserted into its socket. Then, as I always do when I'm repairing an electronic board, I've checked all diode and transistor junctions. In this case, no evident fault has been found. But while looking around on the PCB, I've spotted a broken bypass capacitor. So it was replaced by a similar looking ceramic capacitor, and it's finally time for the first power on. Well, the board starts, but we get this RAM 8 error. Luckily, the service manual for this game has a lot of troubleshooting information, and the error RAM 8 indicates a problem on the 7E IC in the CPU PCB. The 7E IC is a 2 KB static RAM that is almost always socketed, and all socketed RAMs on all PCBs that I've received have been already checked with a good vintage tester. By the way, this IC is the CMOS RAM that is powered by the onboard rechargeable battery that almost always went bad after so many years and may have caused some damages in the surrounding components, so this must be a very common issue on these game boards. So let's check signals on the 7E RAM. And here it is, pin 20 is stuck high. Address and data bus look normal. The chip select signal is called CMOS RAM CS, so let's see where it comes from. This is generated by this other circuit that is meant to prevent false activation of the CMOS RAM when the main 5V rail is off and the RAM is only powered by the backup battery. The select signal goes through a sort of emitter follower made with transistor Q2. That was the one that was cut off from the PCB. I have, of course, checked that the replacement was good before soldering it. We need then to check if the input signal CMOS RAM CS1 is toggling. I've looked on the whole schematic for this signal, but I couldn't find any reference to it, so I've just followed the actual PCB trace and it goes to pin 14 of the Z80 address decoder, and that makes sense. This is also the IC that was newly programmed, but let's check what happens on pin 14 anyway. And yes, it's toggling at each watchdog reset. We can exclude Q2 since it could cause this fault only if developed a short circuit between its emitter and collector pins, but this is not the case. Q3 and these other components are only switching the RAM power supply between the battery and the 5V rail, and couldn't cause the chip select to remain always high anyway. Also, I've checked with the multimeter all the resistors in this circuit and all have the correct values. So the only components left that can cause this failure are the ones circled in red here, and all of them were checked at power off with the multimeter and showed no evident problem. So the only way to understand what failed is to check the voltages at few points. First of all, we should find about 1.1 volts at the anode of CR6 Zener diode. That's exactly the difference between 5 volts and 3.9 volts. This voltage is sufficient to turn on Q4, so its base should be at about 0.7 volts. And finally, we should have no more than 0.2 volts on Q4 collector, since with these values it must be working in hard collector saturation. And in case you're wondering why Q4 must be in the saturation region, it's easy to calculate reasonable values for both the collector and base currents and the minimum gain needed by any transistor to go in saturation. For the tests, I've removed the address decoder IC and grounded pin 14 with the white wire, so I can measure what really happens when the CMOS select is in the active state. Well, 1.18 volts after the Zener is okay. Q4 space at 0.7 volts is okay. But more than 2 volts on the collector. Emitter looks grounded as it should. It's not getting hot or warm. Well, I believe it's faulty. So I removed the Q4 and it was a surprise. Even if the marking almost disappeared, we can clearly see that it's a BC547 transistor. Now, of course, a BC547 can work fine in this circuit. Atari, being an American company, just used a 2N3904 because these were the general purpose transistors more readily available in the American market at the time. But look at this image of the BC547 soldered at Q4. Notice that it's oriented accordingly to the silk screen. Of course, in the Atari PCB, the silk screen is assuming that Q4 will be a 2N3904. But the general purpose BC547 followed the European TO92 pinout that has the collector and emitter pins swapped with respect to the American 2N3904 pinout, as you can see from the datasheet images. In fact, this BC547 is really working fine, but of course it would not do its job when the collector and emitter connection were reversed. Anyway, I've soldered a real 2N3904 transistor in its place now. Now the base voltage is still okay, and the collector voltage is down to 0.1 volts, very good. And now the gain boardset starts fine. As we have seen in the previous video, the board has a test mode that allows to completely test all game inputs. And trigger all the various sound effects. No evident problems have been found, so this was another easy one, it seems. I hope you enjoyed this repair video and that you learned something. If you have any question, use the comment section below. Have a nice time and thank you for watching.